Okay, so first point, midterm is up right now. So if you guys go look, there should be 1 PDF and 2 Excel files of data for question 3, question 4. The Excel files you're going to need for question 1, those were in the previous handout stuff, so those are still part of that page. Current one we set for was Saturday done. Okay, open, what do you guys think? Let's come to a consensus. Would you rather get it over, get it done, get the Band-Aid finished, hand in on Saturday, or take another whole week, one more following Saturday? So again, the way this splits is, yes, you can have another week on the part of it, but warning is work expands to fit all time allowed. In other words, if you have another week, then you've got, I'm expecting that much more time put into it, and rather than procrastinate for the week and then do it at that point. What would you prefer? And open, literally, there's no right answer here. It totally depends on your guys' schedule and what you guys want to do.
I would prefer the extra week.
Okay, so we got one vote there.
I would prefer Band-Aid off.
Band-Aid off, like rip it off, get it done. Okay, so you guys got a head-to-head.
I'm turning it in Friday regardless.
Okay.
I'm turning it in on Friday.
Okay.
Can we meet in the middle and do it Monday?
That's a reasonable compromise, right?
I'll say Band-Aid off.
Band-Aid off. Okay, so hands up for Band-Aid off, get it done, let's say Monday, right? So take the weekend as well. Monday's reasonable? Okay, let's do that, call it done, no point like that. Okay, so fair. Okay, so final point, we will update to, what's that, 14, 15, 16? Feb 16. And again, expectation also for hand-in. PDF, if at all possible, when you hand it in, please do not send me iPhone captures of your handwriting and then paste it into a document. If at all possible, write it, right? Like as much as you possibly can. Especially, I know that equations, does anybody know about like equation editor and stuff like that in Excel? Excel or Word. Basically, take it as an opportunity to do this not as a written document, but as a typed document in some capacity, right? It'll help you out, guys, a lot. But one PDF, any capacity files that you want to sort of put in, graphing and stuff like that, it's up to you guys for what SI should look like. What I would say, though, that is please do follow a name formatting. So what I usually get from you guys is something like assignment 1, or assignment 1 real final, or assignment 1, again, and sometimes there's not even a name on it. So in the PDF name, please put your last name, first name, whatever at that point. At least put your name on the file name. It's going to be helpful. Okay. Where we left off last time was we had bridged over from classic linear free energy relationships, Meyer parameters for sort of nucleophilic or ionic type of coupling, and now bridging over to multivariate linear regression. So this was an application specifically for enantiomeric reactions. And again, the whole point there is there was this open conversation that as long as the energy from your starting material to your product was identical, you could really closely discriminate between the delta G of the two potential transition states. And again, this setup is uniquely available for enantiomeric catalysis, where the starting material and the product in the systems are enantiomers of each other, therefore the energy is the same. The only energy difference is really this diastereomeric transition state, which means you have to have a chiral catalyst that's interacting with some prochiral or enantiomeric starting material. That's where the energy difference is coming in. The other part of this too is you're assuming that your product distribution, or whatever set up this enantio determining event, was a single kinetic step. In other words, whatever step you're taking goes through an irreversible reaction which sets the stereochemistry. So in that way, your product distribution, the enantiomeric ratio you have of your two possible products, can be measured off, which is then telling you something about the delta G that led to it. There's no other epimerization. There's nothing else after this reaction where you're scrambling the stereocenters. It's a nice, clean, form the bond and done. And again, the good news is that's quite a few reactions falls in that bucket, but it is a warning, right? Where if you apply this liberally, and if your product and enantiomeric ratio is not stable over time, it may mean that this is not an appropriate formation. So the original one was these allylations that the Sigmund group dug into. And the focus they were going after was trying to say, can we use this information to tell us about how we might modify the catalyst? And specifically what they were doing is saying, look, this is a very simple amino acid catalyst. It's made up of these modular blocks. That group I've highlighted there, depending on which amino acid you use to form it, you can make one of any possible chiral ligand or chiral catalyst for this system. So the question was, okay, well, let's get some guidance here. What might I be able to do to this group that'll open up possibly better enantiomer selectivity? The model at the time said that that group right here was the main chiral group that was sort of discriminating between the aldehyde. So whatever was in that aldehyde position had some type of a steric interaction that led to one or the other geometry for this nucleophilic allyl fragment. So you're making that bond there across the center, where that's the enantiomer, the two different enantiomeric geometries. And what the implication was that this group here would bump into that group there that then shields one or the other face and helps to guide the product distribution. That was at least the model that was being put forward. Again, one thing I thought was really cool about this is if you look at these conditions, this is kind of one of those kitchen sink. There are a billion individual things going on here in terms of like a manganese reducing agent, bases, catalyst concentrations. There's tons of stuff. And what they were focusing on was we're going to keep all of this constant and we're just varying that substituent so that this way, again, for anybody who's been part of enantioselective reaction development, you know, it's pretty easy to say any non-natural amino acid or natural amino acid could be made up, but the number of permutations you could go after is almost infinite. So it still feels very hopeless to sort of say, well, where do I go next? So this is where what the Sigmund group did is say, based on this group, we're going to come up with a graphing system against what was called the Charton value. Charton values were just a measured constant which sort of captured the steric volume of some group. It was a numerical scale that said certain functional groups have been assigned certain Charton values based on, I don't remember where this ground was. Does anybody remember? Has anybody heard of the Charton values before? It's a physical constant, so they must have done something like, in order to set the Charton values, either it's numerical, what they're doing is they're physically saying, look, I will measure isopropyl and then it'll do a cone angle from it based on a DFT calculation, or it's experimental. They would have had to do something like a reference experiment that is sensitive to sterics, and they're basically putting it on that chart. So I don't remember specifically where the Charton value came in, but it was either, it's going to either be an experimental value saying, look, most isopropyls have approximately this angstrom volume based on that size, or again, it's a reference value back to like a spectroscopic technique or something. Suffice to say that they could say methyl, ethyl, isopropyl, T-butyl, and mantle in this position had reference Charton values. So that would say that, okay, based on that, we're going to take the Charton value of that group. That's what informs these individual lines along this interaction. What we're then doing is saying different substrates are along these angles. So for the simple aldehyde, originally, sorry, that's not that one. The blue in here, this methyl ketone, is this one right here. So that's the methyl ketone. This one right here is that aldehyde up here. And then finally, the sort of more remote one, this remote one here, is this more flat one down here. So each series of lines is a substrate. So just like the Meyer parameters, what we're seeing here is individual entries along the sort of the Charton value, x values. Those correspond to a specific group in a specific ligand. Each line is a series that you're actually extracting against a certain substrate. So the first thing that came out of this that was super impressive is, okay, look, there's a linear correlation. And what we're measuring here on the y-axis is the log of the enantiomeric ratio. Remember, kind of like to the linear for energy relationships. If you take a log, in this case, of the ER, so that's the ratio of one product, the R product over the S product, we're assuming since that's a single transition step, the ratio of your two concentrations, R over S, is equivalent to the ratio of the KR, KS. So it's the ratio of the two reaction constants which means it's really tied back to the delta delta G. So it's that same part that you're measuring the ratio of two concentrations. You're assuming that since it's a single step, that the two K values are being expressed, which then comes down to a delta delta G. So it's still a log of a ratio, in this case, of the two concentrations back to an reaction constant. So that's your y-axis, your x-axis, your Charton value. What we get from this is, number one, let's start with the aldehyde. So the aldehyde on its own, first of all, it gets you to the highest EE values. Second is the aldehyde series and the phenyl ketone series are reasonably parallel, right? So what we're saying there is that two parallel lines means that you've got sort of a similar effect as we move through or change the things we're doing on our x-axis. So as I go from methyl to ethyl to isopropyl to T-butyl in that ligand space, I'm getting a similar enhancement in enantiomeric ratio. Both of them are downshifted, right? So the methyl ketone at the bottom compared to the benzaldehyde, all benzaldehyde values are higher relative to the methyl ketone, but they're kind of offset by a constant. So the two things you can read out of that is, as I change this group here, its impact and energy is reasonably the same through this series. What we're saying is the slope is the same as we go through that part, roughly. That offset represents the impact that the common group, in this case, going from our methyl to our hydrogen, leads to this offset that we're seeing here. So going from hydrogen, we have less steric encumbrance, good selectivity. Adding that methyl group to my substrate, I drop all the values by some constant value. Again, you could extract this and say something like adding that methyl in the place of the hydrogen, it either adds a certain degree of reactivity change. I think the way that this was interpreted out is that methyl basically creates a certain steric bump into your ligand, which is just getting to poorer selectivity. In the end, right, if you think about this, it's starting to define a shape of your transition state that might allow you to see these kinds of results. The last thing that comes out of this too is if we go through and change, let's say, this group for this group, that's where you're seeing this drop overall in your slope. So now what's happening is this massive drop in slope, kind of again, back to our linear free energy relationships. We're saying that by removing that phenyl group, by making it much more distal to my carbonyl, I've removed as I go through and change the size on my ligand, I'm having less and less of an impact in my discrimination. So basically, without having that phenyl group right nearby your carbonyl, the ligand can't tell you or can't give you a major benefit between the two sizes. So this pattern is giving you some sort of a visualization of what transition state makes sense. And like I said last time, the coolest thing that I saw about this kind of work is, let's say, here, let's get rid of all this crap. Let's say you're a grad student. Let's say this is basically the substrate that you have to do. Maybe you went through and did a model substrate on this one first, and you see that, okay, the model substrate's performing really well, and I can get a pretty good bump in enantiomeric excess as I go through this permutation of different ligands. So switching this over from the easy to access isopropyl up to the much harder to make adamantyl has a very large bump in enantiomeric excess. You can look at this and say, I now can look at this on a return on investment point of view. If I spent 3 more weeks making the adamantyl catalyst, I will get a really high bump in enantiomeric excess. Maybe it's worth my time. Versus this same series down here, what you can see on that lower series is much slower slope. So once again, the isopropyl catalyst, easy to get. Let's say the adamantyl catalyst over here takes you a month to make. Is that minor bump in enantiomeric excess of your product worth a month of your time building that ligand in comparison to, you know what, I'm going to make the racemic product and I'm going to split it using classical resolution or something else. You could start looking at this in terms of strategy and say, is it worth the fight? Especially back to this too. Has anybody done non-natural amino acid synthesis? You can buy like isopropyl, right? That's just valine. Cool. T-butyl, that's tertiary-butyleucine. Everybody uses that. The adamantyl starting material, that is a special kind of hell. It's one of those parts that as you jump over to this particular one over here, it doesn't help. There's so much synthesis that goes in behind this. And again, I think everybody who's ever played in this kind of space has had that point where mentally it seems like it's so easy. I'll go to more bulky, but this would a kind of study like this can shut down a particular synthesis of your ligand just because, again, it doesn't predict that there's going to be an outcome that matters. It helps you to inform your potential return on investment. What Matt did next, though, okay, so this works fine with this one system. He believed, cool, chart and values will solve all problems. As long as I know my chart and value, I could potentially extrapolate to any particular system. So in the last example, we're using the chart and value of a group on a ligand. Here, they were doing the chart and value of a group on the substrate. And what they're doing is, with this standard peptide catalyst, they're doing a remote acylation out here, right? So what you're doing is desymmetrizing this remote phenol where the group that you're actually putting your chart and value on is in that backbone piece, right? So we're desymmetrizing very far away. It's still a steric encumbrance. It's a very different reaction class than the last one, right? The last is a nucleophilic addition to an aldehyde. Here we're talking about, some type of a peptide catalyst wrapping over maybe a chiral acylation or something. I'm not exactly sure the proposed mechanism through here. But the simple outcome of this that was, as you went through and changed the size of that group, the chart and value of this group over here did not predict your outcomes. So here, if I change that group, I'm getting a scatter where, larger values, larger steric values seem to have higher EE, but I don't have a predictive outcome anymore. So all this just says is that the steric encumbrance on its own was not enough. There's something else going on here that we have to go through and actually scope or scale. So this is where they went back and said, well, look, chart and values just was one way that we could potentially describe the descriptors for the catalyst, or for the substrate. And again, you've seen this before. We had, para values versus meta values. The para values are mainly focusing on resonance effects, but there's some induction built into it. Meta is induction only. So by going through in different descriptors, you can isolate, call them different molecular features for why a certain outcome exists. So what they decided here was, look, we can describe this R group in a bunch of different ways, not just the normal chart and values. And what they did is they actually basically just creatively said, what is every possible measure we could put to this value, to that group in terms of its steric bulk? What are the other numbers we can apply to? One thing they came up with was sort of 3 different descriptors ended up mattering a lot more. One was this what called the B1 value. So that's saying from the center of wherever that group is attaching out to the minimum distance, if that was a hydrogen. So basically, if you imagine this was an isopropyl group, going from the center to the shortest internal distance was called B1. B5 is the center to the largest value. So now you have a discrimination that actually says a tertiary butyl group, for example, is going to have a tertiary butyl group is going to have an identical B1 and B5 because they're very close, right? Because they're symmetric radially amongst all 3 axes. Versus something like isopropyl is going to have a very short B1 and a very long B5, right? At the same time, there's sort of if you turn this group and look onto its axis, so if this is your attachment point, going across here gave you what was called the L value. So if this was a phosphine, you can imagine that what this is almost like the cone angle. So from the point at which the attachment group attaches to the rest of the molecule to the very back of it, if that L value is very long, what you're talking about is something that might be a phosphine that's very distal, very far away from how it's binding, compared to something where if it's very short, you may have a very tight bond between the phosphorus and, let's say, the metal, which then brings that steric, whatever its steric volume is on that ligand, much closer inside, right? So this is where you could have a T-butyl group, and depending on how weak that binding is or how tight that bonding is, you're taking that same steric volume and drawing it in tighter to wherever center of mass it is. This is just sort of 3 potential ways to sort of talk about steric thing, where really what we're talking about here, this goes back to like A strain values you guys saw in first year. Even though we take a group like a methyl, which looks small, the methyl group has a much higher A strain value than most sp2 centers, because an sp2 center, yes, it can be very big if it's presented this way, but if you turn it sideways, It's actually getting out of the way of whatever other steric encumbrance there is. So it's a way of acknowledging that molecules are not all radially symmetric. You can actually rotate conformers that take large amounts of steric bulk and kind of get them out of the way versus having something that's radially symmetric around. It basically acknowledged that certain transition states need a bit of flexibility where, as part of the approach, you might need to rotate the steric group out of the way to allow the approach to happen, and then only once it's actually assembled into the transition state that steric encumbrance helps you discriminate between two sides. So it helped to kind of balance this idea that just being too bulky to prevent the reaction from happening at all may not be the right way to fix everything. After they'd featurized these molecules in this way, all they did is just carry out a multivariate linear regression. So we talked briefly about this before. On Wednesday, can you guys bring your laptops? We're going to practice in Excel how to use Excel Solver to do basically this kind of part. So all you're doing here is they said, look, I don't know which values matter, but I'm going to go through and take all of my data, my predicted delta G values, which remember is back to your enantiomeric excess, against your actual measured delta G values, and then you're just going to walk through and swap in and out the coefficient for a whole bunch of these values. So in fact, what they're doing is they're saying, I am going to assume that some equation defined by this straight line exists. I'm going to try and minimize my R squared value for all of my energies, and I'm basically just solving for the coefficients in front of each one of these values. And they literally just give something like an Excel solver free rein to make that number anywhere from, I think in this case, they usually sort of locked it in as from +1 to -1, basically. And all it's doing is just walking through different permutations, searching, saying which values can I put in here that gives me a straight line. And so in this case, the equation that they ended up solving, most importantly, there's an overall coefficient. That's just an offset value. We'll talk about that in a second. It turns out that the B1 value has a coefficient almost equal to 1. The L value had a coefficient of -0.1, so it's reverse and it's kind of small. But most importantly, B5 doesn't feature there at all. That's equivalent to saying that the coefficient for B5 is 0. So any value that you can sort of set to 0 means that that coefficient is negligible, not part of the actual solving part of it. So that encoding, what you get from that is, again, putting aside this sort of parameter for a second here, what we're saying is the B1 value matters a lot. And having a specific B1 value that's the right size, or changing that B1 value, has almost a one-to-one correlation to the observed outcome. So that's something you want to tune, in making that, a certain value will give you your best response. L also kind of makes sense. It's negative because the longer we stretch this group out, the more that cone angle is effectively going to be less important. What we're saying is, even if I had a bulky group and I was allowing that L group to stretch out, what's going to happen is that bulky group isn't really seeing the substrate. So shorter L values are good, but it's not the biggest thing in the world. Having a negative just means shorter is better, and then having 0.1 just means it's less important. It's about 1/10 as important as the B1 value. So it gave you guidance. What this let them do is say, once I have an equation that looks like this, I can now go back to any synthetic substrate, calculate substrates that have the appropriate B and L value, and I could say, well, how do I find a substrate that might put me over here? So again, why I was geeking out over this, when like linear free energy relationships in general, it's probably what pulled me most into PhysOrg. The coolest thing about this is it's the only technique that allows you to jump off the page, right? Everything else we do takes a data set and says, within the data set I measured, what would happen along this function? Even like the kinetic fitting that we do, we say, I've measured a couple of points, but I'm guessing what happens inside a data set I already understand. That's the Meyer parameters and stuff. This was the first time that somebody started asking, well, look, I think I have a correlation that's working. How do I extrapolate outside and actually go off the end of my trend and just say that, look, I have some type of a linear trend that's doing this. How do I go over to experiments I've never done before and predict a particular kind of an experiment, right? This was a way of actually using data to generate a hypothesis to test next. Since those early days, Matt then spent 10 or so years, slowly building up both computational and experimental parameters that described all stuff. And again, when we talk about this, the kind of parameters, if you look at some of these early ones, they may not make a lot of sense. So for example, computational stretches or measured IR stretches, fine, that's a value you can ascribe to a substrate. It might tell you about something about like how tight or weak a particular bond is. It tells you about electronic density and maybe things like electronegativity or electrophilicity. NMR shifts is telling you about local density of both conformation but also dynamics as well too. Buried volumes and stuff, these are completely steric kind of parameters. But you can start getting to sort of weirder things too, like NBO, electron density, sure tells you a little bit about what's going on the surface, but some of the other parameters they put in were things like molecular weight, which intrinsically doesn't seem to have any chemical value to it as it is. There's stuff that goes into it, but really what they were just trying to say is, let's not try to go in and come up with a parameter that may have a physical meaning to start with. Let's do the opposite and basically find which experimental outcomes are correlated to whatever we can measure. I don't care what the number is. It could literally be lot numbers at sigma, could be something you put in place as a potential thing you're correlating against. The discipline they were trying to come up with first was, let's find every single numerical ranking that we can come up with that takes a representation and turns it into a numerical scale. And then after saying it was up to them, once they'd found a correlation, to go back and figure out why that particular correlation had any physical meaning, right? And it was really that outcome that mattered. That's what led to this. This was one of the biggest groups, biggest papers that came out in Nature in this kind of area. So this was the work that Jolene did with Matt. The thing that was really interesting here was this was the first time he took this philosophy of, I will go and parameterize one reaction and put it much more generic. So instead of just building a correlation energy delta G versus delta G for one particular reaction and one particular catalyst set, they jumped out and said, look, imines are common as electrophilic targets. Acid catalysis is common with imines. So I'm going to look at totally different nucleophiles that span that space. So instead of just saying I am doing nucleophilic addition of, let's say, enamines or other potential nucleophiles, it was, could I actually extrapolate and say a common intermediate here is any iminium with this chiral catalyst might be involved as a nucleophile-electrophile coupling. So again, the cool jump was you could actually train this data set on things from hydrogenation reactions using ionic hydrogenation species, as well as nucleophilic addition like carbon-carbon bond formation. So these are very different reaction classes, which starts to get at this problem that they had before. Back over here, they were like, okay, we found this great thing for like a carbon-carbon bond formation with these kind of chromium catalysts. That data set was totally unable to tell us what's going on over here because they're different enough reaction sets. This was the first jump to say it's possible that within a finite amount of reactions, general reactivity parameters might exist. That means we can actually jump between totally different reaction classes, not just one for hydrogenations, one for enamine catalysis, and one for iminium catalysis or something else. So that was a big deal. We hired her because of that. The really cool thing is with this generality, you now had the ability to come up with these much more complex parameter sets. It allowed you to say that, okay, if I'm now looking at a new reaction class, you could potentially train it on data from hydrogenation and then use that data to predict what you might need to do for a nucleophilic coupling of an enolate with a wholly different catalyst class, potentially. So this is where the reactivity and general parameter stuff that I think that the Reed group is doing now is really where this starts to cross over. The cool thing about this particular generation was they were able to, for the first time, take a sort of representative catalyst class and then using these parameters, go back and say, if I vary these groups or this group over here according to this equation where we're actually going through and manipulating those values, come up with a brand new substrate that meets those criteria that might give me an enantiomeric excess. And again, especially back in the previous example, this was a case where you're not just looking for, okay, there's racemic, this is R selective, but potentially you even have S selective as well too. So you can potentially look at this and say, I can actually look at the entire sequence of an enantiomeric space and potentially come up with a catalyst that I need on demand effectively. So pretty cool sort of next jump. And again, you guys are the ones that know this part in a lot more detail, but the real emphasis here is that what we're starting to see, this combination of linear free energy relationship and multivariate linear regression really does give you this opportunity to sort of do hypothesis generation here. Now in the space of applied ML, this is really powerful because you can take, let's say, an equation like this, feed it back to a tool that would then come up with synthetic hypothesis. So basically, one algorithm is going to go through and just do the chem draw for you to come up with possible structures, compute those structures to say, does it meet my equation, yes or no? What's my hypothesis for where I'm going to be on this surface, and then potentially go back and only validate a couple of examples with data to then refine your training set. So you sort of have the first version of, at least for enantioselective catalysis, what we used to do for like docking analysis for peptide binding, right? Like if you look at things like AlphaFold and things like this for like peptide component, you take a tool like AlphaFold and then dock potential substrates into it. That's one of the best ways we have now for generation of novel medicinal chemical leads. This is the equivalent here, where we can say for a brand new reaction we don't really know a lot about, we can come up with a hypothesis of what the transition state might look like, build an energy relationship like this, and then use that to start a research and design sequence to figure out what other substrates we would be coming up with. Last one to mention is that Matt has been a very busy beaver. They have now come up with, this is even out of date, but the Kraken database is something that we participated on with the Esper Guzik group. But effectively, he's covered PP ligands, PN ligands, NN ligands, different components from different azides. It's an ever-growing sort of digital ecosystem where, leading off of what we saw with the Meyer databases and the Hammett parameters, this is something now that has become a focused, dedicated library development. Sigmund Lab actually maintains this in a fully open format, but it's still very much driven by a certain research problem will pop up, that area gets featurized, and it sort of grows from that one too. But it is something that if this kind of stamp collecting is really interesting to you, we need more people to help us out with this because it's pretty heavy digital right now. There's a lot of other things that need to come into it from experimental validation from that point, and that's where the automation stuff that we end up doing sort of crosses over. All right, any questions on that before we jump over to temperature effects? I hope you guys talk about this in more detail. So the last point with other manipulations of K, we've been talking about rate constants and how they impacted mainly by substrates or reaction catalytic and reaction energy surfaces. The last thing is temperature. And honestly, this is one of those areas that people don't, it's hard enough to get a really good extraction of a K value at a single temperature. Most of the time, if you can do it at a single temperature with a single set of substrates, that's usually your full PhD. People don't usually take the next step in doing that whole same sequence at every single temperature within a point because it's like a 2 to the n problem. It's hard enough to get a comprehensive extraction of rate constants under a single isothermal point, but jumping over to temperature is very valuable in terms of what it can teach you. So we're going to talk a little bit about some of the historical applications here. First is Arrhenius. So as a quick reminder, remember temperature is the average kinetic energy in a system. It's obviously related back to having a certain amount of energy in a system gives us the ability of a certain fraction or percent of the molecules that have enough energy to get over our barrier. So this is the basics of transition state theory, where we're saying the reason that reactions run fast or slow is not because they don't have on a fixed amount of energy. What you have is a global distribution of energy, and then by changing temperature, all we're really doing is changing the fraction of molecules that have enough energy to surmount the barrier. This is one of those cases where the way you should think about it is the total histogram of all molecules and how much energy each molecule has. At low temperature, we're just saying that it's centered about some lower value. At higher temperature, all we're doing is shifting this energy to some higher point where we're filling in or basically sliding over to that component, right? We're not moving, don't think of it as like a center peak where we're moving that Gaussian distribution back and forth. We're squashing and stretching a balloon where we're lowering the lowest kinetic energy point and then slowly populating these higher modes. It just means that that's why kinetic theory works this way, is because we're looking at the behavior of many, many, many molecules, not on average one molecule at a time, but it still really rests in sort of collisional theory. We're saying that at some point we're measuring the average amount of energy in a system and we're redistributing that energy amongst other components. In general, this is the shape within sort of normal temperatures that we probably end up dealing with. In general, reactions sort of increase with temperature, and there's a kind of a rough rule of thumb where about every 10 degrees you change, you're going to get a rough doubling in the rate. This is kind of, again, it's not perfect, but the reason that sort of sits down is to say within the sort of normal kind of, room temperature up to about 100 degrees or so, this is basically the behavior that we're seeing right now. In the end, that behavior is just given to us by the Arrhenius relationship. The Arrhenius equation is just your empirical derivation of how your rate constant K changes for different points. Again, you guys have seen this before, but if you had to sort of put your own words to the two parameters, A and EA. So Boltzmann distribution, temperature, K, those are all things that you guys know. EA is what? So how is that different than delta G double dagger? Like, because activation energy here, this came before all of that. So again, if you had to sort of, what are they different by, or why are they different from each other? Similar.
I think one of them's like delta G double dagger would be dependent on temperature, but I don't think activation energy is different.
Yeah, like in the end, in order for this to really work, you kind of have to assume that that's temperature agnostic, because you're using an equation to describe how the rate constant changes as a function of temperature. So you shouldn't have another temperature dependent thing in there. So that's true. Well, let's go back to A. What is A? Yeah.
Effectively, from what I know, a structurally based factor that describes how often that collision in the right orientation is going to take place.
Yeah, like this came from transition state theory, where we're saying for the same reaction that has the same activation energy, not all collisions are going to be productive, right? This was a way to sort of say, let's say an SN2 reaction, even if it's an SN2 on a secondary center versus a primary center has less trajectories that might actually lead to a productive attack, rather than something like an SN1 where many other geometries allow. So you're right, the A was basically called it's a probability, basically. What you're saying, and that's meant to capture things like conformational dynamics, right? A primary center can have a lot more free conformers, where more of those conformers will lead to the right, 180-degree nucleophilic attack, compared to maybe a rigid secondary center. You've got less of those. So at the exact same temperature, even if the energy of activation is identical, the probability of a productive reaction is lower because you're just banging into it the wrong way. Is kind of the way that is the best way to sort of think about it. Yeah, EA basically tries to capture mostly enthalpy, right? It's talking mostly about bonds broken and bonds formed, but it doesn't really capture entropy that's in the system. That's kind of captured in this probability argument. So it's a good empirical thing that says probability of attack and the bond breaking and forming, which is really this EA kind of parameter. That's mainly that's stuck in here. Jumping over to Van't Hoff, right? We needed to find a way to sort of to expand this out, to actually break out the enthalpy and the entropy for a reaction to get it over to the delta G, right? So the Van't Hoff equation does a better job of saying, all right, we're going to focus in on both the enthalpy and entropy to bring it into this kind of Gibbs free energy kind of conversation. This is just that symbol derivation of your Van't Hoff equation. If you're ever doing things like solubility kinetics and stuff, this is really important, right? Because solubility is really just an equilibrium constant. And you can sort of extract that point out for things like lattice energies. All I want to mention on this is just, again, normally this is the world we play in. That's what the shape of it is. It does look like, though, that as you keep increasing temperature, this is going to go off to infinite. If you expand this and actually multiply, draw this equation over a large enough range in Ks and temperature, it eventually goes asymptotic. At some point, this equation starts to camp out, and then you're not going to see anything else. So it's just a quick reminder that we're not saying that at infinite temperature you start seeing molecular fusion, or at least according to this point. This is just saying that, for most of what we are doing, we're on the very small end of the curve over here. And then eventually there is a sort of a capping where you're starting to see temperature effects. We're not going to cover it probably in this course, but FYI, watching how you deviate from Arrhenius is one way that you can start to see things like tunneling. So heavy atom tunneling and stuff is actually best seen because if you start to deviate from Arrhenius, you need to find a way that you're getting reactions that break this kind of transition state theory. So deuterium atom tunneling or heavy atom tunneling is only really able to be pulled out by these Arrhenius sort of deviations. So quickly, the I-ring one, why it sort of matters, and this is a derivation you guys may have seen in previous years. I just want to quickly walk over it because it actually comes from what we did in the first couple of classes around pseudo-steady state and pseudo-equilibrium arguments. What I-ring did is say, look, if I look at this profile, and I'm going to hypothetically imagine that my transition state is kind of like an intermediate. So instead of saying, even though we know that the transition state has no lifetime, it's not something you can isolate, his jump was to say, well, if I consider from my starting materials to my transition state as a rapid equilibrium, and then from there to my products is a single K value, I can now separate it into an equilibrium component and a single irreversible component, K. And why this is valuable is because we had math that says, all right, well, the overall rate of this reaction, where the K value there, I can actually express it two different ways. The rate of this case is going to be, remember, second step. So if I do my steady state argument, this second step here is the concentration of my transition state. Again, weird idea, but just go with it. The concentration of my transition state multiplied by this K, the second step, is what I would get if this was a normal two-step process. I mean that it means I can also express this concentration here as an equilibrium. It's just products over starting materials. So the capital K value, how I approach the equilibrium, is given as my normal equilibrium constant. My second step of this reaction, this is my from an intermediate transition state out to product. And that means I can actually isolate and get a term for this transition state concentration, which is just given by this equilibrium constant against here. So I can sub that back in to this value to give me this expression. And again, it looks similar to what we've done before. There's sort of this composite K value and then the starting material concentration. So this is following the same philosophy that we did for algebra around how we do steady state rate dependence. So now that I've got those, you can actually express this out as, okay, I want to go and separate this where I've got just isolation of my K. So now what I'm doing here is I'm manipulating this out to try and get an expression that talks about my rate constant K, and now that I've got things like my equilibrium constant and other components that rise to the transition state, those are things that classical theory has a temperature dependence based on. We know that the approach, this value here, can be described like this from the Boltzmann and the Planck constant. So that's a description of sort of reaching this excited transition state. And then if this is an equilibrium constant, well, equilibrium constants follow our normal sort of delta G equals minus RT ln K. So I have two different equations. Both of them have a temperature value baked into it that allows me to express how the overall reaction constant might actually be manipulated by temperature. And again, this is just sort of a walk-through theory of, based on things they did understand that had a temperature equivalence, how could I come back to the fundamental kinetics and say I need to express K as something that I can manipulate with temperature. And they're just breaking it up into this equilibrium and this rise to excited state way was a way of doing it. So the I-ring equation is really just that sort of that logic and then substitution to get you to these particular values. That's where it sort of comes out. In the end, it looks a lot like the Arrhenius equation, right? You've got your K, you've got some sort of a temperature in this exponential factor. It's just now what we've done is kind of done a better job of defining what A is. Instead of just saying A is for any reaction, A is now based on other constants, in this case the Boltzmann constant and the Planck's constant. So you didn't have to measure it for every single reaction. You had something that had a universal constant associated with it. The other thing too is that it's now changing your EA, where you're getting this delta G double dagger. So what's happening effectively is we've done a better job of saying A is not reaction specific. It's now linked to fundamental constants. And by squishing that A value, you squish up the enthalpy and entropy into this delta G, not double dagger. So that's fun because we can play the same game as the Lineweaver-Burke, right? I can now take my delta G and split it into delta H and delta S. So we can break it out into those two components. This just means your exponential factor here expands, where we have an individual term associated with both. And now we can go through the same thing we did with Lineweaver-Burke, or these other kind of ones where I can linearize this by actually spreading this out. So the more common one you've seen probably for the Eyring equation is if I take the natural log on this side and divide by 1 over t, I can get a linearized form of this one. So this is where plotting ln k over t against 1 over t is just the linearized version of the Eyring equation. So again, once it's set up like that, you can be like, okay, the slope will tell me something about my enthalpy in the system. So the negative slope is related to your delta H term. And your entropy comes from the intercept in that case. The intercept gives us the actual direct value that's associated with your delta S. That's all super fun. Now that you've got these two, you've got a way of sort of extrapolating back to those points. Now, what it means is we could go through and do a series of reactions for some simple system. I can measure the K at a bunch of different temperatures. And if I then plot ln k over t on my y-axis, I plot my 1 over t on my x-axis, I find my linear fit, and from there, your slope gives you your enthalpy value. In this case, for this particular Claisen rearrangement, it works out that you're getting a value of 29 kcals up to your activation energy, and that's reflective of how bond breaking and forming is happening, and it actually fits pretty well with normal sort of thermodynamic theory. What was fun, though, is that you could actually use your slope to actually get this example back to your entropy units. So this is where you're saying that for this particular transformation, that extrapolation predicts that this is a negative entropic value. So what we're going to talk about next really is to go into what the meaning of these guys are. So just but off the cuff, having a reaction with a negative entropy. Remember, what we're saying here is this is the thermodynamic parameters to approach the transition state. So first of all enthalpies, most transition states are going to be, you're breaking things, right? So these are going to be positive values, you're going up. The entropy value though, what does that kind of mean to have a negative entropy associated with your transition state?
The transition state might be more rigid than the overall molecule, so it might be that ring is closing the process before opening back up.
Yeah, so you're saying there's a reduction in entropy, there's more structure associated with it. Yeah, that's one way. Yep.
Probably unimolecular.
That's the other one too. So first of all, most transition states are an ordering of some kind, right? You're taking species and you're actually taking all rotation and flexibility, and you've got to make it into what is usually a very finite number of vibrations. So most entropies are going to be negative. The degree to which they're negative tells you a little bit about, okay, having a very small negative number means that maybe this is unimolecular, because all it has to do is rearrange on itself. Something like SN2, you've got to bring multiple species together into a very ordered transition state, and you're actually reducing the degrees of freedom of multiple different materials. So exactly, the degree to which you have a very finite number of possible transformations is going to give you a very, very large or small entropy value. And this is where that A value comes back. If you have to have a very particular orientation of atoms, you're going to have a massive negative number. That was reflected in the A value, that most transitions were not going to lead to products because of a very particular reaction trajectory that was necessary. So they do kind of correlate to each other. Okay, I'll see you guys on Wednesday. Again, bring your Excel there. We're going to play around with some of the values for doing the fitting associated with this.